Welcome to the 26th episode in the mathsonlinetuition.com videos where we're going through the C2 book. We're on Differentiation Chapter 9. We previously met differentiation at the end of C1 where we simply went over how to actually differentiate. But now we're going to start talking about how we can apply some of those methods and appreciate differentiation a little bit more. 9.1. You know the difference between increasing and decreasing functions. So here you have a graph. In this graph we appreciate that there is an interval between A and B where X is between A and B, and without loss of generality, if x1 is less than x2, then the function fx1 is going to be less than fx2, and it follows that f dash x is greater than 0 in this interval, meaning that as it increases between these 2 points, if x1 is less than x2, so it goes from a lower coordinate to a higher coordinate, then we have that the function increases, meaning we have a positive gradient. And I'll show you an example here. So if we have this, so say this is A, this is B, you can see that this is going to be a positive gradient. Why? Well, because it increases. Say we had a table now, so a graph where A and B, and it goes as such, then this means that we will have a negative gradient. Okay, so please bear that in mind. And the same is mentioned here with regards to a curve that includes both types of gradients. So you can see that here the gradient would be positive, and then as we go down the gradient would be negative. So a curve does not have to be exclusive to any one. Here is an example that you're asked to resolve just by looking. So 3x squared plus 24 is this equation differentiated. Now x squared is always going to be positive because anything squared is positive. Multiplied by 3, which is positive, and 24, which is positive. So we know that the differentiation is going to be positive, which means that fx is an increasing function. And likewise here, example 2, you see the same thing. X cubed plus 3x squared minus 9x. If you differentiate it, well, we can appreciate that taking factorization for this new equation here, we get x plus 3x minus 1, which means that x is going to be minus 3 and x is going to be plus 1. Okay? Some more examples for you to do. Now here are some properties that we need to appreciate. The points where fx stops increasing and begins to decrease are called the maximum point. The points where fx stops decreasing and begins to increase are called minimum points. A point of inflection is a point where the gradient is at a maximum or a minimum value in the neighborhood of the point. And finally, points of zero gradient are called stationary points, and stationary points may be maximum points, minimum points, or points of inflection. What does that mean? Let's use this graph to explain. So, taking the first point here, the points where fx stops increasing and begins to decrease are called the maximum points. This is fx, okay, the curve itself. So as it increases here, see it's getting higher, 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 higher. This is A, and it begins to decrease now, which is evident just by observation. So this is called the maximum point. Likewise here, the origin is a point of inflection on this curve. Why? because as you can see, it stables out, so it becomes horizontal, okay, and then it's at a gradient. The gradient is at a maximum or minimum value in the neighborhood of the point. This is again a point of inflection, and then you can see that we are decreasing once again, and then all of a sudden we start to increase. So this is a minimum, okay. You can have a number of maximum points and a number of minimum points, depending on the characteristics of the equation. Now, don't be confused by the fact that you could have a number of now, evidently this would be a maximum, but don't be fooled into believing that this is not also a maximum, and this is a minimum, whereas this is also a minimum. So minimum here does not mean the lowest, and the maximum does not mean the highest point. No, rather what it means is that there is a point where fx stops increasing and starts decreasing, and likewise here fx stops decreasing and starts to increase, okay, just to point that out. And then it says here that a stationary point is also the name used for a point of zero gradient are called stationary points, and stationary points may be maximum points, minimum points, and points of inflection. So if you're asked find stationary point, okay, where f dash x equals 0, okay, or df equals dx equals 0, they mean the same thing. This is the function f, and this is the coordinate point x, okay. So f differentiated with respects to x equals 0, okay. I remember why it's 0, because the gradient has to be leveled. So here you can see that at the turning point it's level, turning point is level, turning point is level, and at the turning point here it's level. Why? This means that we will have the gradient equal to 0. So, as we can appreciate, the stationary point is going to be a maximum point, a minimum point, or an inflection point. Okay? So it could be either one of these three, and it will be up to you to figure that out in an exam. Now, this is another few points to consider to find the coordinates of a stationary point. So first you have to find dy dx, i.e. f dash x, which we've already mentioned, and solve the equation f dash x equals 0 to find the values or the values of x. So if you have, say here, 3x squared plus 5, sorry, minus 5 equals 0, this is just an equation I came up with in my head just now from examples that I've done previously. You were to bring that there, have 3x 5 x 5 3. So 3x squared minus 5, you bring it around. So this is and you have squared there, it's going to be 5 plus or minus. So you have two x's here. Now what you then go on to do is, so on a graph you'd have, say, 5 over 3 square rooted minus 5 over 3. This is the x coordinates. You'd plug this back in to the original fx, okay. In our case it would be x cubed minus 5x plus c. Now I don't know c in this particular case because I was made up, but you'd have some c. If you plug it in here, you'll get the fx, or the y is another way to represent it. and then having the y will enable you also to have the coordinates. Now if you were to differentiate this further, okay, you would be able to figure out whether it's a maximum or a minimum. Okay, and we're going to describe how. So just going on to this example here, example 3, we can see that they have, like our previous example, x to the power of 4 minus 32x, differentiated it, equated it to 0. Now then they have rearranged to find x. X is 2 here. They've plugged it back into y. Then once they found their coordinates, they know that this is a stationary point. What does that mean? It could be a maximum, it could be a minimum, or it can be a point of inflection. They use a little bit of a different method here, which is quite tedious in my opinion, but they know that x equals 2 going to have gradient 0, it's going to be flat. They take 2 slightly less than, they take x less than 2 here, for example 1.9, they get that the gradient is minus 4.56. okay, so they have that the gradient is negative. Then here they take x which is greater than 2, they, for example 2.1, and they get that the gradient is 5.04. so they've taken the x, they've put it into here, and they get their result, whether it's positive or negative, and then they can illustrate using the curve how the diagram will be constructed, and then you can see that the shape that it forms indicates that it will be a minimum. Okay, this is a bit of a long method. I like to use what is written here. You can also find out whether stationary points are maximum points, minimum points, or points of inflection by finding the value of this, when necessary differentiating it 3 times at the stationary point. Okay, and this basically means that if dy dx equals 0, okay, then dy squared d squared y dx squared, if it's less than 0, okay, that means that it's a maximum. If dy dx equals 0, d squared y equals dx squared is a minimum. Okay, and then we have that if d equals 0 equals 0 and dy does not equal 0, we have the inflection. Okay, so what this means is simply that, I simply put that when you take your values of x and y, okay, at that stationary point, so if you have stationary point, okay, say for example this is a made up coordinate 5 and 6, and there is some fx, okay, whatever that is, okay. Now when we differentiate fx, we have equals 0. Now if we put 5 and 6 into this, it gives us 0. If we put 5 and 6 x and y coordinate into here, it will give us a negative number, so it will be negative, and it will give us, that means it's a maximum. That means 5 and 6 is a maximum. Okay, so this point here, 5 and 6 is a maximum. If it's here, it's a minimum, meaning that if d squared y over dx squared is greater than 0, it's a minimum. And here, if we have differentiated it 3 times for it to have values not equal to 0, then it's a point of inflection, and it can appear as such. Okay, so here's another example for you to appreciate the grand scheme of things. We have this cubed equation, it's differentiated. Now once it's differentiated, it is factorized to extract the values for the stationary points or the coordinate points, which are maximum, minimum, or a point of inflection. We can see that we have x equal to 4 and 1. So when x is equal to 1, we put it back into the original equation to get our y coordinate, and we do the same for 4. So it says that we have 1 and 17 as one stationary point, and 4 and minus 10 as another stationary point. So the next thing we do is we want to find out whether it's maximum or minimum. We've differentiated this. This is what the result we get once it's been differentiated twice. So using both equations in their own turn, we have x equal to 1. So now you can see there's no y coordinate because we can appreciate that it's just x being used here. So we have minus 18. If it's minus 18, that means that it's going to be obviously maximum because it's less than 0. Now if we put in x equals 4, we get 18. So this is greater than 0, which means it's the minimum. And that's simply all that we know and all that we need. So now we can find out, and we can say comfortably that this point here, okay, is a maximum point. So it increases and then it starts to decrease. And this point here is a minimum point. So it's decreasing, and then when it gets to that point, 4 minus 10, it starts to increase. It changes its direction. Find the greatest value and state the range of the function. Okay, so here we're being asked to find the greatest value. Because we know that it's a cubed graph, okay, it's only going to have one peak. So we can see that if we differentiate this, equate it to 0, x will be equal to 3. Okay, now the greatest value of this quadratic function is 9, and the range is given by fx is less than 9. So that means that this here, if we differentiate this again, so what we will have is minus 2. So d squared y dx squared is going to be minus 2, which is less than 0, which means it's a maximum. So that verifies the fact that it is the greatest value. And we can also appreciate that it will be at the point 3, 9. So x is equal to 3 and y is equal to 9. Here we're going to use a 9.3 take some practical, applied principles to utilizing differentiation. So you can see that we have this sector of a circle, we have some information, parameter, and you're asked to find the area. Okay, so you can see, show that A equals such. Now we know that the parameter equals this, sum of the two radii, 2r, and an arc length mn. This is something that you should know. Rearrange and substitute. So all we've simply done is rearranged and substituted p equals 100 from the value, from the information we were given here, and then the area of the sector is going to be this. And now we've already shown this before from our previous chapters, and we substitute it in. Now once we substituted it in, we have one unknown, which is the r, and that cancels out to give us, with the r outside, cancels out with the r inside. And so you can see that this is the result that we have here. So we know now what the area is, which allows us to move on to our next question, which is asking us to find the maximum, okay, and show that A is the maximum. So again, we differentiate it, we get that this is the equation, equal to 0, r equals 25. Differentiate it again to find out that it's negative, which indicates that it's a maximum. Now C, substitute r into 25, so the value of the angle for this maximum area, and you get this particular value because we have the equation for the angle and all the information that is required. And then we can find the maximum value of the area again by using this formula, this equation. Example 7, a similar thing. You have all this information here. Show that the volume V of the tank is given by this. Again, this is taking all these different values and formulas, rearranging them, and then you're able to find the answer by differentiating in part B, and then again differentiating once more to find out whether it's a maximum or minimum. So everything that we have done before. And you have some more examples to do here that you can run through to give you that sharper eye and ability to complete more difficult tasks. We have the mixed exercises, and once again summary of key points. The summary of key points you should memorize because it will outline all the important properties you need to appreciate. The ones that we've discussed here about the maximum, minimum are important. Discussing what stationary points are, what it means to have a point of inflection, also how to utilize both methods of taking values before and after the x coordinate to show the value of d squared y over dx squared, or alternatively differentiating twice to give us the value of d squared y over dx squared. And then you have this written out neatly and some more information. So thank you very much for listening. I hope to see you again next time for chapter 10. Take care and goodbye.